Okay, so we're going to talk about the equilibrium constant and how to write the reaction quotient. So if you take a look at what we have here, we have a reaction or a general model, again, for a balanced equation, all right? And what this is going to do is going to be pretty much like the equilibrium constant. All we're going to do is we're going to change one or two things. So for one, the reaction quotient is represented by the QC, okay? Like the equilibrium constant, you're going to do the products over the reactants. So the little lowercase here times D divided by the concentration of the reactants. Okay, B, and that's going to be lowercase b. Okay, so here's really the only difference. Now, when do you use the reaction quotient versus the equilibrium constant? Well, let's take a look at this graph. This graph right here shows you kind of similar to the one I showed you the other day, okay? And here you have at the beginning, yes, the reactants are at a high concentration, and then at the other end, you have the products at a low concentration. Now, this is before they're mixed. As they become mixed and the reaction moves in this direction, right? You're going to have this reaction happening over a course of time. So as you have the reaction happening in this direction, the concentration of the reactants are beginning to decrease as the concentration of the products are beginning to increase. Now, there's going to be a point right here, and this is, let's say this is at about 20 seconds, right? Where the concentration of the products and the reactants become equal, okay? So at this point, this is what we call the equilibrium. Okay, this is where everything stabilizes. Now, all the area here, right, all the area to the left of the equilibrium, this is before equilibrium. I'm going to abbreviate EQ, right? So everything before the equilibrium is represented before they stabilize. Now, when you are before equilibrium, then you write the reaction quotient. Once the reaction has reached equilibrium, then you write the equilibrium constant, okay? You write the equilibrium constant. So let's take a look at this graph, and let's see if we can write a balanced chemical equation using reactants A, B, and product C. So we can see that over the course of 20 seconds, we have a decrease from 0.5 to about 0.3 for this one. Right? Let me see if I can, where's my pen? So it's not to scale, but let's assume that 0.3 is about here, about halfway, right? So we'll call this 0.3. So you can see that over the course of the 20 seconds that we have a decrease of 0.2 moles for reactant B, right? And we have a decrease here from 0.4 to 0.2, also at around 0.2 molar or 0.2 mole, sorry. Now, the product, on the other hand, in those same 20 seconds has increased by a factor of 4. So that means that this guy is 2 times the reactant, right? So because it's 2 times a reactant, then the mole ratio is going to be a 2 to 1. For every one that decreases, this one increases by 2. So if I was to write a balanced chemical equation, then the reaction would look like this. It would be A plus B produces 2C, right? So let's say this is our balanced chemical equation. Now, if I was to take this one and I was to write the reaction quotient for it, all right? So let's go up here. Let's write the reaction quotient. Or let's see, yeah. Let's do that one first. So I'm going to write the reaction quotient. So for this one, it would be QC is equal to C2 over A times the concentration of B. Now, if I was to write this at equilibrium, which I'm going to abbreviate EQ, then the equilibrium constant would look pretty much identical. Except the only difference would be the equilibrium constant symbol. All right. Now, when you're writing the reaction quotient or the equilibrium constant, remember that the products are always over the reactants. So let's take a look at an example. Let's say I have a reaction that says lead chloride reacts with, or actually decomposes, to lead 2 plus ion. This would be in solution, plus 2 moles of chlorine ions, also in solution. Okay? Now, when you're looking at the reaction quotient, you need to pay attention to the states. This is in solution, this is in solution. Okay? What you need to remember is that when you're writing the reaction quotient, pure liquids and solids are not included. They're not included, okay? The only thing you want to include is going to be states that are in solution, AQ, or in gas. And we're going to get to gases in just a minute. So when you're writing the reaction quotient, right, when you see a solid, ignore it. You're not going to include it. Or if it's a liquid. So the reaction quotient for this would be QC is equal to the concentration of lead times chlorine ion 2 plus. Okay? This equals the reaction quotient. All right, there's your reaction quotient. Okay, let's see you're working with equilibrium. With the partial pressures of gases. Okay, so in this situation, now we're talking about partial pressures. Now, to this point, here's what we got. We got that the QC is the reaction quotient. Okay, the Kc is the equilibrium constant. Okay, now when we're talking about gases, well, now this is written as QP, and this is written as KP. And this has to do with the partial pressures of gas. Okay, so let's take a look at an example. I have a reaction that says nitrogen gas reacts with 3 moles of hydrogen gas. All right, that goes to equilibrium to produce 2 moles of ammonia, which is also a gas. Now, in this example, all 3 of these are in gases. So how would you write the QP, the KP or the KC for this, right? So in this situation, it would not be the KC, right? If the question is asking you for the KP does not equal the KC. So make sure that you're paying attention to that. All right? So I'm going to write the KP for this. There's 2 ways to write it, okay? The first one says you can do it exactly the same format that we've been doing, which is NH3, right? You're going to signify that it's in gas, all right? And then you're going to square it because it's products over reactants. Then you're going to write it as the concentration of nitrogen, right? Also, you're going to write that it's a gas times the concentration of hydrogen, also a gas. Okay, this is going to be cubed. Okay, that's one way to write the Kp. The other way to write the Kp for this is to write it in terms of the partial pressures. So this one says that the partial pressure of ammonia gas divided by the partial pressure of nitrogen gas times the partial pressure cubed of hydrogen gas, okay, is equal to the Kp. All right. Now, both are acceptable, but I think the AP exam prefers this. Okay. So that's the difference between doing the equilibrium constant of when you're working with molarities, and this is when you're working with gases. So that's it for today.